I will be talking about deforming representations of the Morava Stabilizer Group. And while the previous talk was full of wonderful theorems that I really appreciate and enjoyed, my talk will have no new results. So I'll be mostly talking about some old work of Mazur's on deforming Galois representations. And what's new here is hopefully potentially a new perspective and lots of questions that I want to ask here to you all. And so if you have thoughts and ideas or recognize some things, do let me know. So this is sort of the beginnings of a project joined with Robert Dix, who is a number theory graduate student at the University of Illinois, applying for jobs. So if you have an interest in hiring number theory people who are interested in homotopy theory, check his application. So, right, so then the other disclaimer that I have is that sort of the theme of this workshop, the spectra, and triangles, and higher structures, will not be very much explicitly appearing in my talks, but here's my attempt at a joke, is that the specter of homotopy theory is haunting us all here, is haunting everything that I do. Okay, so let's get started with some math. So what I'll have here is a profinite group, G. And we'll make an assumption about this group that it's sort of reasonable enough, finite-ish enough. So the formal name for this is that it satisfies something called finiteness condition phi p. So here the specter is making us like choose a prime. So we always we start homotopy theory talks by fixing the prime p. So essentially we're satisfying finiteness condition phi p, which means that for any open subgroup of finite index inside of G, we have that, say, the first cohomology group, continuous cohomology group, that's the coefficient, is finite dimensional. Or something about it being finitely topologically generated, or at least after P completion. So the examples, well, all finite groups satisfy this property, but there are two sort of profinite group situations that appear, and so the first one is the example of actually Galois groups, which is what Mazur and followers have studied, and these are sort of deforming Galois representation is a whole world out there. So these would be the, say, absolute Galois groups of some Galois group a number field, K, unramified outside of some set of prime sets. So this is the original example. Okay, and I won't say much about this because I just don't know enough to say about such things. And the second, or first, that's the zeros, example 0, the one and only example that I will be focusing on really is this Morava Stabilizer Group. So I'll say something more about this later, but this is the sort of, well, it's not really one group, it's a family of groups. And what they are, they're automorphisms of formal group over some field A. Finite field.
Also, if you have a finitely generated group and you take the pro-P completion, that will be another example, right?
Yes, exactly.
So the definition is there exists a zero such that.
No, for all open subgroups, we have finite generation of the pro-P completion of the open subgroup. All right. Yeah, and so what else we're going to have? We're going to have a K will be a perfect field, and maybe let's just take a finite field to make life simpler. And what we're going to have is a residual representation over this finite field K. So what we're going to try to do is deform this representation. Okay, so suppose we have say A is a complete Noetherian ring, or maybe more classically, one starts with like a local Artin algebra. So then we ask the question, so and with residue field K, so deformation of this row bar is a lift of it to A. So we have this quotient map. So this is, I'm supposed to, I'm formalizing what I mean by deformation. So deformation of row bar to A is a lift, like that. And we take these notions up to an isomorphism, except now we're looking at it up to strict isomorphism, and here we're strict equivalence, and strictly equivalent means equivalent by conjugation with matrices that are congruent to one modulo the maximal ideal. So these are up to strict equivalence. So in particular, Rho bar, when I say it's a representation, I really just mean this homomorphism. And then rho itself can have conjugate matrices in the kernel there. Set that here. And I want to write this down to introduce the notation for the kernel up to conjugations in, so I'll write that as gamma n of a, the kernel of the GL n of a. This is visible enough. Okay. All right. So the theorem due to Maser, this is from 1987. Is that this deformation functor is representable, or the functor. Okay, I did not say what the deformation functor is, but we can guess. So suppose, so actually Maser supposed that the rho is absolutely irreducible. However, so what that means is that after any algebraic extension, it's still irreducible. However, the representations I will be caring about later are not. But thankfully, I guess this is an improvement due to Ramakrishna. A few years after this, is that, or at least that the endomorphisms of rho bar over the root G are just obvious ones. So in this case, and then the functor that destination functor from C, which are these complete local Noetherian rings. Two sets. DSA is the set of these strict equivalence classes of deformation. Rho bar through A. So this thing is representable. So it's representable, which means that there's some ring such that D of A is mapped from R to A. So this R has a universal deformation.
Complete the local Noetherian ring R.
Yeah, yeah. And the proof of this theorem is that a sort of direct and pretty straightforward application of Schlesinger's criterion.
The morphisms in C are all local homomorphisms that could be identity on K.
Yeah. So yes, so these are, yeah, I mean, there's, as is usual, there's sort of, you know, we could have these to be with residue field K, and have a deformation problem that fixes K, and an analogous deformation problem that does not fix K, and there's going to be some Galois actions and so on. But yeah, so let's just work with those that fix K, like local homomorphisms. Okay, so I don't need to erase yet. Okay, very good. You know, like, okay, so I'll start with the first example, which is actually, if you look at characters, so one-dimensional representations, then you don't need the fancy representability theorem. We can actually spell this out and see what has to happen. So let's do that. So suppose we have a character from G, let's call it pi bar, to the units in K, and then we're trying to lift this to the units in A, right? Okay, well, the units in A are going to be equivalent, isomorphic to the units in K, and then we have this, and then units which are congruent to 1 mod the maximal ideal. And so there's a lift here that gives us roots of unity in A, and then the question of, maybe I should make it solid because we know that exists, and then the question of lifting chi, so chi is then determined by a map to the units congruent to 1 mod the maximal ideal. By homomorphism from G to 1 plus MA, this multiplicative group. And then one thing we observe is that as a group, this is an abelian Rotary group. So if we're trying to write down a map from G to something like this, we know in particular that will factor through this unionized Rotary completion of G. And really we're just looking at this homomorphism from that to the units congruent to 1. And I wish I had more space on the board at this point. But basically this tells us what the deformation rate is in this case. It's the group, the completed group algebra on this G-ab P. Still the same tool. So then the corollary of this, the sort of brief elaboration is that for any character, the universal deformation ring of it is this, let's see, say, A is P to the R, then we can join the P to the R minus first root of infinity to the p-adics, and that's to this, and form the group algebra here. The universal deformation is then chi of G is chi 0 of G times the class of G in the group algebra, where chi 0 is this trivial lift.
So what is the z p to the r minus 1? It's
So the p temporal So these complete algebras that have fp to the r as residue field will be algebras with the shrink. All right. So so in the examples of groups, then when we take these, okay, so suppose we took G to be the Galois group of the rationals, and we're looking at extensions only ramified above P, then sort of we're in the world of class field theory, and so for this G, the abelianized P completion is 1 plus PZ inside of the p-adic units. And so that's R. Note here, the ring itself does not depend on the character, but for the universal deformation does. Then this thing is polynomial power series algebra on one generator. In the example 1 of the stabilizer group, now I'll tell you more about this. My best friend, the Morava Stabilizer Group. So here's an explicit description of this group. And previously it said this is the automorphisms of some formal group law, and somewhere, there's a choice of formal group law, but, it doesn't matter for the purposes. Yes. Sorry, what was that?
Okay. We're all just reacting to the noises you
Okay, so there's going to be a so we're going to form this ring. I see. So now I'm going to start writing a letter that's kind of almost like N, but it's H. Okay. So this has nothing to do with higher structures. But maybe it does, I don't know. That spectra of homotopy theory is also, you know, like there's deals that we make with them about, you know, if you want not to suffer, you have to also choose a height, and so we choose a height. So this H is some integer variable equal to 1. And there's, I said there were formal groups, and if you're a formal group person, you know there's a classification by height. So, but the triangles have also something to do with that. Okay, so anyway, so there's this non-commuting variable that we adjoin, but it's not like completely non-commuting. We're going to ask that if you want to commute an element here by S past, then we have to act on it by the Frobenius. And again, so this ring here actually has, you know, has Fp to the R as its residue field, and it has a unique lift of Frobenius. So P is the unique lift of Frobenius to CPTR. And there's another thing that we're doing here. S is actually an H how do you say, root of P. Okay, and then we take the units in this algebra. So this is extremely explicit, and you can do a lot with this explicit description. So one thing you could do, or maybe, you know, is either do this yourself or look up suitable reference. For example, Vesna Stojanoska has a notes on like a mini course on the Morava Stabilizer Group. What you will find there is a computation of what G ab P is. This is going to be, so there's always the special treatment needed for the prime 2, but if P is odd, we have one copy of the p-added integers and then H copies of Z mod P. And when P is 2, there's an extra copy of Z mod 2. Because, well, why not?
For H equals 1, this is the classical fact about multiplicative group of
exactly. Yeah. So that fact sort of perpetuates itself and causes complications. You know, it's the key troublemaker in sort of chromatic splitting conjecture and things like that. So anyway, so as a consequence of this calculation, we get that universal deformation rate of characters of this group is going to be now looking like over, and I wrote R here, but I really mean H. So this H and that H need to be the same. So these are characters. You know, yeah, we're looking at representations in fp to the h. And actually, maybe we don't need to. Anyway, let's just do it that way. This needs to be done to h. Anyway, no, actually, you know what? Here I don't need it. I can do anything here, but there I do need it. So now we're going to have this same sort of, okay, the ZP is going to give us one sort of free variable, and then we'll have h or h plus 1 variables that just p power 7. So, you know, you could say, okay, well, right, now what do we do with this, right? That's the question. So I have sort of conclusion slash a question here already. So this is telling us that if we are trying to deform our character to rings which have sort of interesting p roots of 1, then we get to have sort of weird deformations. Then sort of I ask myself, like, what sort of information do we get from that that may be useful in homotopy theory?
Can you explain why it's important to study deformations of representations of this group?
Yes, I'll get to that. Yeah, thanks. I have that planned a little bit later, so maybe I won't switch around the order in case I miss something. Yeah. Sort of. So what kind of I don't know conclusions do we get? So you know, maybe I don't know. So like exercise is like find good uses of this to, say, studying the card group of the Campbell homotopy theory. And one thing that happens there, maybe I'll mutter that while I try to erase the next board, is that, so here we're talking about p roots of 1, and it's a well-known fact to people who ever think about this in homotopy theory that you don't get to just do that. It's usually you destroy a lot of structure when you try to adjoin p roots of unity. So, all right, well, you know, while we're still at characters, another remark here is that if we actually have any old representation rho bar, or any you know, these residual representations, you know, in any dimension, well, we have the determinant of rho bar, which is a character. And this determinant map tells us that the universal deformation ring of this rho bar is an algebra over the one for the determinant, which actually, you know, yeah. We said this ring does not actually depend on the representation. So this is just an invariant of the group itself. So we have this additional structure for these deformation rings. All right. So going back to general dimension. It's not that big, but I want to give myself some space. So we're looking at rho bar from G to K. We're trying to make this here. Okay, so let's study how we can do this explicitly in order to sort of understand what our instructions are to lifting. So we said gamma and, okay, here's the kernel. And we could look at the kernel of this rho bar. You know, this is now a finite group. So we have some, this is, the kernel is an open subgroup. And if we have rho, then we can, you know, like these U's act trivially. So that means that they land in this subgroup of matrices congruent to 1 mod the maximal ideal. So rho dashes are a little bit weak. So if we have rho, we get that rho tilde, which is rho restricted to U, is this map to, so it's from this U or the kernel rho bar to gamma and the base. And this group is now, this is a pro-P group. So that means that this map factors through the pro-P completion of U. And so it turns out, as far as I could tell, in the sort of number theoretic applications, when we're looking at Galois group of number fields, for some specific choices of, you know, nice representations here, what happens is that the pro-P completion of the kernel of that representation ends up sort of reducing the group quite a bit.
I don't understand. So why U is a subgroup of finite index and G?
Yes.
But why is it not pro-P complete already if G is pro-P complete?
G is not pro-P complete. G is a pro-finite group. If G is pro-P, then so will be U.
Ah.
But G is not pro-P. So our G here is very close to being pro-P in that there's a map to the units in Fp to the H. And of course, the units in Fp to the H is not a P group, so it's not pro-P. So we have a surjection to there. And the kernel of that is a pro-P group. I guess my comment here is exactly that the group I'm interested in is very close to being pro-P. In particular, the representations I'll be looking at do have this property that U is already a pro-P group. The comment I was making is that in number theory, it seems like a lot of things get simplified about this crazy Galois groups by taking pro-P completions, because there are just not that many extensions which are pro-P, with pro-P Galois groups. Okay. So, for example, Mazur gives some examples of representations that are built from sort of curves, two-dimensional representations, and the deformation rings are then computed to be these completed power series algebras, just free, on some like 3 generators. And, there's no relation, so a very nice deformation ring. In the example I'm actually interested in, there are, so then U, so for our examples of interest, and I'll say what the representation is, then U will be already pro-P. So there are 2 things. So for G being this group SH, there are 2 things on which this group naturally acts. So the first thing is already up there. Okay, so we said G is the units in this algebra. So we could just take this algebra and act on it. So O, I guess, well, and we could call that OH. Not to write it again. So OH is the algebra. So maybe I should write like O 1 over N or something, or D, whatever, doesn't matter. OH has a really nice action, and let's say if we do by right multiplication by group G, that's actually so this is so with the action of G by right multiplication. So making the choice of side here has to do with trying to have actually representation that's ZP to the H linear. So this thing is defines GLH versus ZH. Okay. So the great thing about this representation is that we can understand it really well. Like we can take an element of our group and write down the matrix that it acts by. Okay. The second thing is the thing that this spectre of homotopy theory wants us to study. That's related to another deformation problem, the Lubin-Tate deformation problem. So I said that this SH is actually the group of automorphisms of some formal group law of H over this field FP PDH, and that acts on the deformation problem of deforming this formal group law to similar sort of complete algebras or Artin local algebras. So it's acting on this Lubin-Tate deformations. Let's call this H sub H, which is the Honda I'll just vaguely write it like this, and then and so this is why, right? This deformation problem is the thing that's been, it's the basis, in some sense, of chromatic homotopy theory, and that's right. So this is the, finally I get to a point where I cannot avoid saying Quillen's name. So thanks to Quillen, we know that we know that there's a strong relationship between stable homotopy theory and formal group laws. In particular, this classification of formal group laws by height tells us about the filtration, let's say, on the stable homotopy category. And one of the key players there is the deformation ring, the Lubin-Tate deformation ring of these formal group laws of a fixed height. So the deformations of this deformation problems for some fixed formal group law is representable. So this is Lubin-Tate. This is representable, and the ring that represents it is computable and extremely nice. So I'm calling it E0, which has these universal deformation parameters U1 through H minus 1. And these, that's right, so why I'm writing E0 here, because then by Gores, Hopkins, Miller, maybe Devinitz Hopkins, probably also say Morava to sort of signify, like, okay, there's several statements here. I'm also doing the thing where I'm summarizing like 30 years of mathematics in one sentence. There's a spectrum E H. So generalized homology theory, which has an action by this group S, let's say, and the Morava statement there is that he saw the following, that the sort of the K local sphere, KH local sphere, is the homotopy fixed points of this action. Well, we also need to take care of some Galois group of this F. So this thing here, this story is central to chromatic homotopy theory, and one of the things that we really want to do is understand like we know that, just because these are all factorial things, we know that the stabilizer group is acting on this ring. And so how do we describe this action? So we want to understand how Sn, Sh acts on E star, which is the homotopy groups of the spectrum, of which pi 0 is the E0, the Lubin-Tate deformation ring, and this is sort of E0, and then there's another variable in, so there's an even periodic ring spectrum. And this is, it turns out this is extremely hard, but there's one thing that we know, is that, so this is by Vesna Stojanoska. Is that if we take this pi minus 2, so of our ring E, which is kind of like E0, but maybe it has a little bit twisted action because we're multiplying by U. Okay, well, maybe I don't quite understand what the action is there, but if we mod out by P and the square of the maximal ideal, so here the maximal ideal in E0 is generated by P, U1, and so on, UH minus 1. So this thing actually is isomorphic to our example 1 mod P. And the next thing that we know, and 2, is that this is not the sort of, this isomorphism is not, so this is equivariant isomorphic. And however, so we would like to be able to say, well, then, we have some sort of algebra going on here. We could, so here's something that we would like to have. We would like to take the symmetric algebra on this OH, complete it suitably. Maybe there is some an analog of this U to be adjoint so that we can spread ourselves around in various graded degrees. And we would like to say, or maybe I need to adjoin the W and then complete and then sort of, so we would like to say that something like this is exactly pi star P. Equivariant. But what Edwards and Hopkins showed is that, well, it's not actually quite true. This is only true, something like this is true, or maybe something exactly like this is true, after passing to divided power envelopes. And so that involves declaring that sort of powers of these variables ui be divisible by powers of p. So it's kind of hard to use this. And anyway, but so my inspiration for looking at all this stuff is this first observation is sort of telling me that, well, maybe pi minus 2 and this OH are deformations of the same residual representation. And then you sort of ask, okay, so now what happens, like can I classify all deformations and study that to find a different comparison potentially, or maybe find this comparison somewhere in the world of deforming the representations. And to do that, so what I would need to know to do this specifically is to know some cohomology groups. So out of this sort of Schlesinger's apparatus come a relationship between these deformation problems and some cohomology groups. And so, you know, if you know how to compute H1 and H2 of the stabilizer group with coefficients in the adjoint of this representation of this OH mod V. Let me know. So, I mean, I've been trying to do this explicitly, and I'm finding it hard. You know, this is sort of like translating one really hard problem into another really hard problem. So this is so anyway, I want to advertise this as a question and a problem that I'm interested in, and if you have any clues on how to approach this question, you let me know. Okay, I better stop. Thank you.